Hello, my name is Hee-Duck Oh. I'm a PhD student at North Carolina State University, working with Dr. Massimo Iorizzo and Dr. Penelope Perkins-Vesey. Texture is a very important trait for consumers. Multiple studies have shown that firmer berries or crisp berries are preferable for consumers compared to soft or mushy berries. Also, texture can be a very important trait for machine harvesting. Machine harvesting saves a lot of labor and time compared to harvesting by hand. Firmer berries are generally considered more suitable for machine harvesting because they are less susceptible to internal bruising. A texture analyzer is one of the instruments that allow you to measure multiple texture components in a very accurate way. There are various instruments available for measuring fruit texture, but not all of them can measure more than one mechanical parameter at a time. A texture analyzer like this one is one of the instruments that are capable of assessing multiple parameters. How it works is that it has a probe that slowly goes down. You could have it to compress the fruit a little bit, or you could have it to puncture the fruit depending on the method that you're using. And then the probe goes back up. The force or the resistance that the probe is receiving from the fruit is recorded along the way in the form of a graph like you see here. The force goes up at first, it's at maximum force right when the skin breaks, and then the force goes down rapidly. After that, it's the internal part of the berry. Different types of probes can be used to collect different types of data. This is an example of a 2mm flat probe. From this probe, you can collect parameters like the maximum force, distance to maximum force, mean internal force, and Young's modulus, and so on. This is a compression probe that's basically a wide plate. It's usually used for compression tests like the texture profile analysis or the TPA. And from this method, you can get parameters like hardness or resilience. We've been also using a needle probe, which has a very sharp tip. It's only penetrating the berry by 2mm, and we're trying to measure the texture components at the very outer layers, like the skin. When you're running texture analysis, the first thing you need to do is calibrate the instrument. The first thing to calibrate is the force, using a calibration weight. We use a 2kg calibration weight to calibrate the force. And then you calibrate the probe height so it knows how high up the probe is above the platform. It goes down slowly, touches the platform, and then goes back up. After calibration, to measure the texture of a sample, you need to run something called a macro. A macro is a sequence of instructions for the texture analyzer, which is set up before your experiments. The macro includes instructions on what kind of information or data to collect from each sample. You can also integrate different devices like a barcode reader, a digital caliper, or a scale, and also you can put in different prompts like what's the name of the sample or the rep, what's the date, and are there any signs of decay, or any other information you want to collect about a sample. To analyze the data from the texture analyzer, you need to use the output file. The output file is a simple Excel file with the parameters that you're interested in. You can change the type of parameters to be included in the resulting Excel sheet. For downstream analysis, you can just use the output Excel sheet like any other dataset you have. You can run analyses on Excel itself, or you can use other statistical softwares as well. The first column of the Excel sheet will have the information of the sample that you put in, like the sample name, the cultivar name, the harvest date, or the experiment name. And the following columns will have the data for each of the parameters that you set up for the macro. And this includes the data that was put in from the devices that you added on, like the digital caliper or the scale. Our recommendation is to use an instrument that can measure multiple texture components and not just one. Blueberry texture cannot be understood by just one component, so it's important to collect data for different components to evaluate different aspects of texture. like the sensorial firmness that you feel in your mouth, or how the texture changes during storage, and so on. Depending on the program and number of seedlings to evaluate each year, if it's not high throughput enough for early stage selection, this could be used at advanced selection stages as well. There seems to be mainly 4 components that contribute to blueberry texture. The first one includes force at 1 millimeter, which is the force recorded at 1 millimeter depth, and Young's modulus. These parameters measure the stiffness or resistance to the deformation of the berry. The second component is maximum force, or FM, and this is the force recorded at the maximum peak where the skin breaks. The third component is the mean internal force, or the MIF. This measures the force while the probe is inside the berry going through the pulp. The fourth component is DFM, or the distance to maximum force, which represents the deformation before skin break, or the ductility. These 4 components could be used to predict both the sensory firmness and the post-storage texture. Maximum force, or FM, is associated with sensory hardness, springiness or crispness that you feel in your mouth when you're biting into a berry. And FM was also associated with consumers' preference or willingness to pay. Thinking about how quickly the texture of a blueberry changes during storage, we wanted to also identify parameters that can help us understand the rapid softening during shelf life. Initial firmness drives the post-storage texture, and we've found some parameters that can explain the variation between harvest and post-storage, like the Young's modulus, F1 millimeter, and DFM. DFM is a rather independent component from Young's modulus or F1 millimeter, but these parameters all contribute collectively to the change of texture during storage. Texture is a complex trait. It has moderate to high heritability, but it's genetically complex. So phenotyping will remain the most effective way to select for this trait, compared to DNA-informed selection. We won't have any molecular markers available for this trait anytime soon because it's a very complex trait. When you set up the macro, you can have it to include a barcode or a QR code scanner like this. You can print out stickers or labels to put on cups with your blueberry samples in it that contains information about the experiment, the sample name, the set or the rep or the date that it was harvested, etc. And the QR code would have all that information in it. And when you're running the macro, you can simply scan this barcode into the barcode scanner and it will record all the information that's included in this code. You can also integrate devices like a digital caliper to measure the stem scar diameter of a berry. And the data that you collect from the caliper will be automatically sent to the laptop or the macro. You won't need to measure the diameter of the whole berry because the texture analyzer will automatically measure the diameter. You can also attach a scale to the macro so that you can send the weight of the berry to the macro, and the resulting Excel sheet would have the weight along with all the texture parameters that you measure for each sample. Compared to FirmTech, the biggest advantage of using an instrument like the texture analyzer is that you can collect multiple texture components of a berry. The texture of a blueberry is a very complex trait which cannot be understood by one texture component. So being able to collect multiple parameters using a texture analyzer can help us understand the texture in depth. Based on recent findings through collaborative research, 4 texture components were identified as the main contributors to blueberry fruit texture, and post-harvest texture was found to be related to the initial texture. Some possible parameters to select for in breeding programs Maximum force, or FM, was the best predictor for sensory attributes of hardness, springiness, and crispness. High DFM led to less overall texture change. High Young's modulus 20 burst strain was related to lower bruising ratio, and larger size at harvest led to less water loss and wrinkling. The macro that we developed to measure these texture parameters is available for anyone, so feel free to contact us if you're interested in using these methods.